Swayam Prabha. Digital India. Educated India.
Is von Neumann's minimax theorem for any zero sum game A, min over y in y of max over z in z, y transpose A z is equal to the max over z in z min over y in y of y transpose A z. So, remember this here, was the upper value and this here was the lower value. Okay. So, we are going to prove this. So what is, before I start with the proof, essentially what is this? What is the claim? The claim then is that the upper and lower values in the mixed upper and lower values are always equal, okay, for every game. And what, as a corollary, what we have is that there is always a saddle point for any game, provided you extend the space to mixed strategies. Okay. In pure strategies, there need not be a saddle point, but in mixed strategies there would be. And in the previous class, I argued what the significance of a saddle point is. That saddle point is a point from which a player would not is a saddle point which such that in which each player plays his own security level, and then after playing that there is no regret, right? The other player would also respond with his own security strategy. So this property holds now in the space of mixed strategies. Okay, all right. So that's what. So this is obviously a major landmark in the theory of games. So this predates Nash's work by several years. I mean, probably it's proved around the time Nash was probably a child. We will. So what I will show you, there are several ways of proving this. What I will show you is a modern proof, it is short and nifty. The original proof is much more complicated, and over time it has been refined, and this is now how we understand is the best way of proving the min-max theorem. Okay, all right. So we need a tool here, which is linear programming duality. So, the linear programming duality basically, so in linear programming we talk of two types of problems, what is called a primal problem and another one which is called its dual problem. So, we write two different optimization problems that are closely related to each other, okay, and we relate they are formulated and crafted in a very specific way, and it turns out that in that case, if one of them has a solution, so does the other, okay, and the optimal values are actually equal. Okay. So, I will write out a fairly general form of linear programming duality here. Okay. So, in its most general form, the linear programming duality can be written in this sort of way. So, you have an optimization problem that looks like this. So, you are minimizing, say C1, your variables are x1, x2, x3. Minimizing C1 transpose x1 plus C2 transpose x2 plus C3 transpose x3, and this is being done subject to constraints that look like this: A11 x1 plus A12 x2 plus A13 x3 greater than equal to b1, 821 x1 plus 822 x2 plus 823 x3 less than equal to b2, a31 x1 plus a32 x2 plus a33 x3 equal to b3. x1 is required to be greater than equal to 0, x2 is required to be less than equal to 0, and x3 is unrestricted. Now this here is a linear optimization over these three variables x1, x2 and x3, and these are the constraints that the variables are required to satisfy. They are all linear constraints. The first constraint is asking for a linear combinations of the x's to be greater than equal to a constant b1. Second is asking it to be less than equal to another constant b2. Third is asking for another linear combination to be exactly equal to b3. And then the x1 is signed constrained to be greater than equal to 0, x2 is constrained to be less than equal to 0, and x3 is unrestricted. This is the most general way you can write out a linear program. Okay, most sort of explicit way in which you can write out a linear program. Of course, you can reduce it to standard form and all that, but our problem, we don't benefit from putting it in standard form. That's why I am starting off with this form. Now, corresponding to this linear problem, we have, remember this problem is minimizing a linear function of x over these regions. Corresponding to this, there is what is called a dual problem. So, if this is called the primal problem, then corresponding to it is another problem which is kind of like a twin problem to this, and that is called a dual problem. So, the dual is a maximization, okay, and it is maximization of again the sum of three linear functions of now another variable, we will call that variable w. So, you are maximizing b1 transpose w plus b1 transpose w1 plus b2 transpose w2 plus b3 transpose w3, and the constraints are that you have a11 transpose w1 plus a21 transpose w2 plus a31 transpose w3 is less than equal to c1, a12 transpose w1 plus a22 transpose w2 plus a32 transpose w3 greater than equal to c2, and a13 transpose w1 plus a23 transpose w2 plus a33 transpose w3 equals c3, and w1 greater than equal to 0, w2 less than equal to 0, and w3 is unrestricted. Okay. So far all I have done is just written out two optimization problems in a very explicit manner. So, on the left you have a minimization problem which is in three variables x1, x2, x3. On the right you have a maximization problem in three variables w1, w2, w3. Now, if you look at the constants of this problem, they are closely related. So, the coefficients in the objective of the problem on the left, the coefficients of the problem on the left is called primal, the problem on the right is called dual. The coefficients of the objective in the primal are actually form the right hand side of the constraints of the dual. The coefficients of the objective of the dual are the right hand sides of the constraints of the primal. Okay. and if you look at the coefficients on the left hand side of the constraints in the primal and the ones in the left hand side of the constraints of the dual, they are actually transpose of each other, right. It is as if this entire thing matrix here has been transposed and formed into a matrix here, right. Okay. There is also some relation between the signs of these x's and the w's. We can come to that if necessary. So now these are two problems that are obviously they have been crafted in a very specific way. You cannot sort of make whatever combinations you want with it. Like for example, this is a greater than equal to here. Okay, there is a less than equal to corresponding less than equal to here. This is a less than equal to, this is a greater than equal to. Okay, the signs of these are also very specifically decided. Okay, now so these are, as I said, very specifically crafted problems, and they enjoy a particular property, and that property is what is called linear programming duality. Okay, so this is the if either primal or dual admits an optimal solution, then so does the other, and so does the other, and the optimal values of the primal and dual are equal. So the optimal values of these primal and dual are equal. Okay, so we are not saying optimal x's are equal to optimal w's, obviously not. There is no claim being made about the relation between the x's and the w's, but what is equal here is the optimal value of the optimization. So the objective value that you get here, it will be equal to the objective value that you get here. Okay. Another thing to point out, remember, is because of the way these things have been transposed and so on, x1 here has, for example, the number of variables x1 is equal to the number of columns of A11, okay, or equal to the number of columns of A21, and also equal to the number of columns of A31. W1 on the other hand is equal to the number of rows of A11. Okay, W1 multiplies with A11 transpose. Okay, W and A12 and A12 transpose and so on. So the x1, x2, x3, these together, the number of variables that you have here, okay, the length of this of x1, x2, x3 put together need not be equal to the length of W1, W2, W3 put together. So you cannot expect a direct correspondence, a very obvious sort of correspondence between x1 and W1, x2 and W2, and x3 and W3. But what is remarkable is you still get equality between this in the objectives. The optimal values of these objectives, provided both exist, provided one of them exists, are equal. Okay, all right. So this is the theorem that we want to use. So we want to use linear programming duality now, and what we will do is we will use linear programming duality to prove this equality that we have here. Okay, this is what we are going to show. So what we will do is the following. So the plan is, we are going to take this left hand side, we write this as a linear optimization, a linear program. Okay, it will correspond to one of these. It will correspond to the primal problem. Okay, so this one will write out as a linear optimization. It will be taken as the primal problem. Then take its dual problem, okay, and show that the dual problem actually is nothing but this problem itself. Okay. So the idea is going to be that we start off with the left hand side, write that as a linear program, consider its dual, which is written out here in this. This is the dual of this will tell us how to write out the dual of this problem. Okay. And then invoke linear program, then show that that dual actually reduces to this problem, and then use linear programming duality to claim that these values are equal. Okay, that is basically the proof plan. Okay, so let's start off with the proof. Okay, so now let's start off with VM upper bar. This is min over y in y, max over z in capital Z, y transpose Az. And remember, we argued that this is actually the same as min over y in capital Y, max over j of y transpose A j. So now suppose for the moment I just put, let's say I put T as this quantity, which is max over j y transpose A j. Then it has to be that T is greater than equal to y transpose A j for all j, necessarily, because T is the maximum, right. Now, one way to write this whole thing is to say the following. So, I multiply, so T is a scalar, right. T is the maximum over j of y transpose A j. So, what I am going to do is I am going to multiply T with a vector of 1s. Okay, so T times 1 is greater than equal to, so a vector of 1. So, this 1 is a column vector. So, I will just transpose it. So, T times 1 transpose is greater than equal to y transpose A. This is a compact way of writing what I already have here. So, what is this vector of 1s here? This is just simply this is a vector 1, a vector with every component as 1. It is a column vector with every component as 1. So, T times 1 transpose is basically a vector, is a row vector with T in all its components. That is equal to every component of another row vector y transpose A. No, for a fixed y. Yeah. So, I have put T, so question right, I have put T equal to y transpose A. I have to put T equal to y transpose, the max over j of y transpose A j. Okay. And I encode this as this relation. This implies that T is greater than equal to this, and that is encoded in this sort of form. Okay. All of this is being done for a fixed y. Now, suppose I asked you again for a fixed y, suppose I asked you what is the minimum T, okay, what is the least value of T such that T into 1 transpose is greater than equal to y transpose A. What is this value? So, if T was the maximum, then T satisfies this inequality that I just wrote. Okay. Now, suppose if I look at any T that satisfies this inequality and look at the minimum such value of T, what is that minimum value? That is actually equal to the max over j, right. So, this is always equal to the max over j of y transpose A j. So, what has happened as a result is that if you look at the inner maximization here, the yellow boxed one, that is equivalent to this. So, we have just established the this relation. Okay. All right. So, now what I can do is therefore go back, and now I was going to write minimum of y over y, max over j y transpose A j. Now that is actually equal to the same as minimum of y over y and minimum of over t of t such that T1 transpose is greater than equal to y transpose A, right. It is a minimum. Is this clear? So, I am minimizing over y this thing, this exact thing that I just wrote out. But then I am minimizing for what am I doing here? If you see this, I am doing a minimization followed by a minimization. So, what that means is essentially I am actually doing just minimization, right. I can combine the two variables t and y and write them eventually as one minimization. So, effectively this becomes actually the minimum of t over both variables t comma y subject to all these constraints, subject to the constraints in y as well as the constraints that are there in t, okay, subject to this t into 1 transpose greater than equal to y transpose A and the constraints that are there in y. What are the constraints in y? Y is just required to be a capital Y is just saying that small y is a probability distribution, right. So, y is greater than equal to 0 and summation of the components of y is this is equal to 1, right. So, is this fine? So, this here encodes, this is my capital Y, this guy has come from here. This together is actually equal to my left hand side, which was nothing but my Vm upper bar. Okay. So, now Vm upper bar has been written in this sort of form. Let us clean this up and so it is a little more presentable. So, what I will do is I will remove the transposes from the first one and I will just transpose the first one. Let us write it like this. Let us write it as t into 1 is greater than equal to A transpose y, and then the other is I have my summation over yi. Summation over y is nothing but, again, because I have this notation of ones, the vector of ones, this is actually nothing but 1 transpose y equal to 1 and I have y greater than equal to 0. And my variable t, which is also a variable, is unrestricted here. There is no constraint on the sign of t. So, only thing you need to really, just convince yourself is that when you take two minimizations one after the other, they are actually just one minimization. Okay, you can just do a joint minimization instead of doing, you are minimizing over one variable first, then minimizing over, keeping the outer one as a parameter and then minimizing over the outer one. It is the same thing if you just jointly minimize both, jointly minimize over both. Okay. Any vector minimization actually is basically a joint minimization over individual scalars. So, that is exactly what is going on here. Okay. All right. Okay. So, we have now written this out. So, what is this now? This is now a linear program. Okay. So, what we have got is that Vm upper bar can be written as simply the solution of a linear program. Okay. And we will take this to be our primal. We will take this to be the primal and we will invoke the linear programming duality theorem that we just wrote previously. Okay. So, we are going to write this as a primal problem in this particular form here. Is this fine? Alright. So, now can someone tell me, if now this is to be taken as the primal, then let us just decide the values. I can write them out here itself. Tell me what are the various variables first. How do I model it in this form? What my y is required to be greater than equal to 0. So, I can take x1 to be y. This is my y. Okay. So, I will take x1 to be y. T is unrestricted. So, I will just take x3 as t. Okay. I will take this to be t. Alright. Okay. Now, let us start with the coefficients in the objective. What do I have in the objective? I have only t in the objective. which means that, so this C3 is 1, X3 is T, X3 is T, X1 is Y. X1 and C1 and C, there is no term in Y in the objective. Okay, so therefore C1 and C1 and C2 are both 0. So there is not, so these are 0. There is also no variable X2 which is less than equal to 0. So all coefficients of X2 can be put as 0. Okay, so all of these guys are taken as 0. Is this fine? Okay. Now let's look at the constraint. Now let's first write out the let's look at the equality constraint first. Okay, let's take this one first. So 1 transpose Y equal to 1. So which means that in my equality constraint here, I have my B3 here should be scalar 1. Okay, so this guy should be 1. Y was X1. So the coefficient of Y here should be 1 transpose, right? 1 transpose means that this A31, this guy is 1 transpose here. A31 is 1 transpose. There is no coefficient for T in this equation. So which means that this A33 is 0. Okay. Let's go back here. In fact, let's write this in the form. Okay. What I'll do is I'll take this, the first equation, I'll actually write this in a less than equal to form. Okay. So that might make things easier for us. So I have this as A transpose Y minus 1 times T is less than equal to 0. Okay. So now this is a less than equal to equation. Since this is a less than equal to equation, the right hand side of that equation is B2. Okay, so this guy has to be less than equal to constraint. So right hand side B2 is 0. What about the coefficient of X1? That means the coefficient of Y, A transpose, right? Okay. So which means that A21 here, this guy is A transpose, and the coefficient of X3, which is A23 is just 1. Is there any equation of the greater than equal to form? Is there any constraint of the greater than equal to form here? There is none. So we can just take all those coefficients also as 0. So all of these are also 0. Okay, so these guys are all 0. This was 0. This is 0. Okay. This is fine. And now what do we know is the dual of this? Then we can read out the dual here. Okay, so let's cancel out stuff that is not that is anyway not that is going to disappear. So C1, remember C1, C2 are 0. So C1, this guy is 0. C2 is 0. C3 is 1. So that is 1. Okay. B1 is 0. B2 is 0. So these are gone. B3 is 1. So this is 1. Okay. A12, A22 and A32. This whole column was here 0. So A12, A22, A32 being 0. That will basically ensure that this is out of question here. This is gone. Okay. All right. What else? A11, A12 and A13 are 0. A11, A12 and A13. So these are all 0. Okay. A33 was 0. This is also 0. let's populate the things that remain now. A21 is A transpose. So, A21 transpose therefore is just A. So, this is just A now. Okay, A times W, W2. Okay. A31 was 1 transpose. So, A31 transpose is now 1. A23 was a vector 1. So, A23 transpose is a vector 1 transpose. Okay. Now, if you see here, what's happened is all the coefficients corresponding to W1 have all disappeared from the problem. So, W1 is as good as not there in the problem. So, this guy is not there. Okay, what you have is W2 and W3. Okay, W2 is less than equal to 0 and W3 is unrestricted. Okay, so let's write this out in a clean form. So, the dual now of this is, this was my primal. So, my dual is going to be, what was the objective? Objective was just 1 times W3. So, it is just maximization of W3, and I had 2 constraints, A times W2 plus 1 times W3 less than equal to 0. So, A transpose Y minus 1 times T, no. So, this here is, this was minus 1, this is A transpose. So, this guy, there is a A transpose here. So, this is to be minus 1. Okay. So, this is minus 1. Since this is minus 1, A23 therefore is also minus 1 transpose. Okay. So, the constraints are that A times W2 plus 1 times W1 into W3 is less than equal to 0. Negative 1 transpose W2 is equal to 1. W2 is less than equal to 0 and W3 is unrestricted. Okay. Now, all I need to do is a small change of variables. Okay. So, let us put from here, put W3 as let us just denote this by W. Okay. And let minus W2 be Z equal to minus W2. So, then in that case, this takes, then the problem, the dual problem becomes max over W A times Z greater than equal to 1 into W, 1 transpose Z equal to 1 and Z greater than equal to 0 with W unrestricted. Now, all we have to do is go back and interpret this problem. Now, you can see here, just looking at this itself. So, I am maximizing this, remember, now over W and Z. Just looking at this already, this is seeming similar to what we had written for the rope layer, for the upper mixed value, right, for VM upper bar. So, for VM upper bar, we wrote a minimization over T with over variables, minimization of T over variables T and Y. Now, here we are doing a maximization of W over variables W and Z. Y was required to be a probability distribution here. Here Z is turning out to be a probability distribution, right? And the T was this T times 1 was greater than equal to 1 transpose Y, right? And here 1 times W is less than equal to A times Z. Okay. So, all I have to do now is basically just reinterpret, I have to interpret this thing, go back and check if this matches with VM lower bar. Okay. So, suppose so let's just do that now. Okay. So, So again, like I did with for the row player. So so suppose if W was min over I of AZ, the ith row of AZ, then we again have that min over I of AZ I is actually the max value of W, such that W is less than W times 1 is less than equal to AZ, right? Is the largest value of W such that W times the vector of 1s is less than equal to AZ. That is actually equal to the minimum smallest component in of AZ. Okay. So, from there therefore, we have that max over Z in Z min over I of AZ I is in fact max over W comma Z of W with these constraints. AZ greater than equal to and this problem is exactly the problem that we got here. Okay. This is exactly what we got. Okay. So, in other words, what have we concluded therefore, that we have concluded that this guy here, this box problem is in fact equal to Vm lower bar. But then linear programming duality tells us that these two are equal. Now, to be exact, actually linear programming duality tells us that these two are equal if one of them has an optimal solution, okay, has a finite optimal value. Now, why do any of them have a finite optimal value? Because the optimal value is in fact their security level, and we just argued that there is a security strategy and a security level for each player. Okay. So, once a security strategy and a security level exists, there is a solution to there is a finite optimal value to each of these, to either and in fact each of these linear programs, and therefore, the form linear programming duality, the optimal values have to be equal. Okay. So, by linear programming duality, these two become equal, and so therefore, we get that Vm upper bar is actually is equal to Vm lower bar. This is von Neumann's min-max theorem. Okay. So, we have basically shown that from here, so that the mix, once you allow players to play mixed strategies, there is the upper and lower values of the game, and in short their security levels actually coincide. As a corollary, there always exists a saddle point. Every pair of security strategies forms a saddle point. Every saddle point is a pair of security strategies, and every saddle point must have the same value. All of these properties we get for free. Okay. Now, just a couple of remarks before I end about the proof. This proof is, as I said, a modern proof. It uses linear programming duality. Linear programming duality was derived in the 1940s, okay, 1944, 46, somewhere around that time. Von Neumann's min-max theorem is 1932. Okay, that is, so it's well before linear programming duality. So, but what's interesting is that, I mean, it was, so obviously I'm giving you a proof that is shorter in retrospect, now that we know the whole language of linear programming duality. So, von Neumann's original proof effectively derived linear programming duality as part of proving this. Okay, so, his original proof is a separation based argument, and he effectively just anticipates linear programming duality and its development as part of his proof. Okay. Okay. So, yeah. So, in other words, all the things that so what have we concluded, that all the things that we realized would hold if there was a saddle point in pure strategies. Now, but a saddle point in pure strategies did not exist, and therefore we were kind of handicapped. Now, all of those things actually hold. provided we move to mixed strategies. Okay. So, in other words, the theory of games for zero-sum games is now stands watertight. We have a solution in which both players sort of think of what the worst case damage the other player could do, therefore play security strategies, and these security strategies are in equilibrium with each other. That each player would want to respond to the other guy's security strategy with his own security strategy. And so, that basically gives us now a watertight theory for zero-sum games.